Hello and welcome to the fifth lecture on machine learning. Today we will discuss Bayesian linear regression but with an introduction through Bayesian estimation. What is Bayesian really all about? So recap the maximum likelihood estimate and the probabilistic interpretation of linear regression. We also saw that the maximum likelihood estimate coincides with the least square estimate, which we obtained through a geometric interpretation. We also motivated a need for incorporating prior, and that was basically to address the problem of overfitting. So prior incorporation for addressing overfitting. We'll see more of that today. So a question is, what is a very intuitive prior for linear regression with its probabilistic interpretation? So when I say probabilistic interpretation, I will mean that the error epsilon is normally distributed, bounded by plus minus 3 sigma as per the 3 sigma rule for Gaussian distributions. So we also saw that one prior for W is that its norm should be somewhat bounded. An intuitive prior that gives you basically a condition such as this is that the components of W should not become too large. One might resort to some prior such as each Wi component is Gaussian distributed with some parameter mean 0 and variance theta or theta square. So question is, how will you use such a prior for posterior? We'll need to understand prior and posterior a little carefully, and we'll do that through an illustrative coin tossing example. We'll discuss what maximum likelihood estimate means for this coin tossing example, and then contrast that with Bayesian estimation. So let's say Suresh likes to toss coins. He decided to count the number of heads and tails in his coin tosses. He tossed the coin 1000 times. Found that the coin landed on heads 400 times and tails 600 times. So what's his reflection? If he were to toss the coin once more, what is the probability that he gets a heads? One would expect the answer to be probability estimate as 400 divided by 1000, because that's what he observed, or rather 0.4. Is that really the case? And how do you get it? So we are tempted to say that the probability in a subsequent toss is 0.4, but why? This is actually a result of trying to maximize the probability of observation so far, rather to compute the parameter or estimate the parameter value that would maximize likelihood. And what is likelihood? It is a probability of the data you have observed so far, but viewed as a function of the parameter. So let the observed data follow a distribution f theta, theta being the unknown parameter. For example, theta is the probability of heads occurring any given toss. Now this theta comes from a Bernoulli distribution, which says that the probability of heads is theta, the probability of tails is 1 minus theta. So let x1 to xn be the set of random variables governing the observation with a joint PDF or a probability mass function, depending on whether they are discrete or continuous. So let f theta x1 to xn be the observation probability. Now this f parameterized by theta, subscript theta, is exactly what corresponds to the PDF or PMF. But the right hand side is what lets us move close to likelihood. Now we have introduced theta as an argument. So we'll see that this can be viewed as a function of theta but subscripted with data set. So I'm just going to complete this and say if this could also be viewed as f subscript x1 to xn function theta. So given observed values x1 to xn, small x1 to xn, the likelihood function of theta is basically the probability function viewed as a function of theta. And the maximum likelihood estimate of this theta is exactly that theta hat that maximizes this likelihood. Now how do you get this? To obtain theta hat, we can make one simplifying assumption which is quite reasonable. We'll assume that the data is independent and identically distributed. So recall that independent means that the distribution of the joint configuration is a product of the marginals. And identical means that p subscript xi, the distribution for xi, is the same p of xi. So the form of distribution is the same, independent of xi. It's almost like in object-oriented programming, the p of xi is a class and the p subscript xi is like the object. So the exact value might be different, but after all, the objects are instances of the class. That's what we've shown here. The maximum likelihood estimate is theta hat, which is argmax over theta of the product of the individual marginals coming from the same distribution. This is where we have made use of the IID assumption. Now that's not necessary, as we will see in the forthcoming tutorial. So coming back to the coin tossing example, we want to maximize the likelihood of having observed 400 heads as outcomes. This can be obtained by looking at all possible combinations of 400 tosses that would have led to the 400 heads, and the remaining should be tails. So 1000 choose 400 into the IID assumption based joint probability of 400 heads, which is nothing but p raised to 400. Similarly, the IID assumption based joint distribution of 600 tails is 1 minus p raised to 600. Now you can verify that for this specific case, the maximum likelihood estimate will indeed be 0.4. In fact, in general, for h heads and n minus h tails, the maximum likelihood estimate is h divided by n. So what is Bayesian inference now? So suppose Suresh brings in a newly minted coin to toss, and being a physicist, he believes that the coin is fair. So the coin has been designed to be fair, and heads and tails are equally likely outcomes. So he flips the coin 4 times. However, he finds that the heads appeared all the 4 times. All the 4 tosses resulted in heads. So would p hat equals 1, which is the MLE estimate, 4 divided by 4, would that be intuitive? Is tails improbable? Well, as per the maximum likelihood estimate, yes, indeed it's improbable. But what about his physicist view that the coin is actually fair? Is there a way that Suresh could update his belief about fairness? Yes, he probably doesn't want to stick to fairness assumption anymore, but could he avoid going to the other extreme of insisting that the coin will always yield the heads? So let's try and develop some jargon. So Suresh starts with a hypothesis and his hypothesis that the coin is fair. So it's one of several competing hypotheses that he has subscribed to. So what he could do in general is come up with the prior probability of heads before the data D is observed. So this is the prior probability. This is a prior belief in the hypothesis. However, once he observes the data, his distribution over the possible hypothesis is subject to change. And how? Well, this is as per the Bayes rule. So what is Bayes rule? Probability of heads given data, or hypothesis given data, is probability of data given hypothesis into probability of hypothesis. This is a joint distribution in the numerator divided by probability of data. Now, why are we ignoring the denominator? Well, the data or evidence is already observed. So for the posterior, or probability of heads given data, probability of data is simply a normalization factor. So we'll ignore it and let the integral of probability of head given data give us the normalization factor in any case. Now, one more point before we get into specifics. What is the desirable form of probability of data given heads? So if the probability of data given heads follows a distribution D1 and H follows a distribution D2, what we would like is probability of the hypothesis given the data, the posterior, also follows D2. So D2 is the conjugate prior of D1 if the distribution, the posterior, follows the same distribution D2 as the prior. Are there examples? Yes, indeed. So if your prior P of H is chosen, if the probability of data given H turns out to be Bernoulli or binomial, an appropriate prior to choose for the hypothesis is beta, so that the posterior also follows beta. What is beta? It's a particular distribution which we will talk about. There are several other examples. On the left hand side you might see some of your familiar distributions. For example, Poisson is familiar. The conjugate prior for Poisson happens to be a new distribution called gamma. In this course we will come across Dirichlet for categorical and multinomial case and beta. We might not come across the others. What is the beta conjugate prior? So the conjugate prior for beta should look somewhat seamless to be integrated with probability of data. So if probability of data given H is written as a product of number of heads, p raised to number of heads, 1 minus p raised to number of tails, what we would like is the probability of heads also to look somewhat similar, p raised to something, 1 minus p raised to something. Why? So that when I multiply the two, I'll get p raised to something plus h 1 minus p raised to the other thing plus 1 n minus h. So this is what I mean by seamlessness. Will the normalization factors take care of themselves? It turns out so, and that is exactly the case of the beta distribution. So a conjugate prior for Bernoulli is the beta distribution where the numerator is p raised to alpha minus 1 minus p raised to beta minus 1, and the denominator is a beta function or the beta normalization function. This beta function is again written in terms of gamma functions, which behave somewhat like the factorial function. So it turns out that when alpha or beta are integers, then gamma is the factorial function as defined here. In other cases, it behaves somewhat like an interpolator between the factorial functions applied at different integral values. So what is the posterior? The posterior basically is proportional to the product of the likelihood and the prior, which we have actually written here. And as anticipated earlier, we would like p exponents of the p's to be able to add up and give something intuitive, exponents of 1 minus p to add up and give something intuitive, and we would like the normalization constant to adjust itself out. And that turns out to be the case. So we'll get p raised to alpha plus h minus 1, 1 minus p raised to beta plus n minus h minus 1, and the normalization factor actually gives you the beta normalization function. So the overall posterior looks like this. The alphas appear like the number of heads expected before the entire experiment began. Beta look like the number of heads expected before the experiment began. All you have done is added to your expectation the actual counts. Just to become convinced that this is indeed the case, if you take the expectation of p under the beta distribution, it turns out this is alpha minus 1 divided by alpha plus beta minus 2. I'm sorry, the minus 1 and minus 2 aren't there. The mode of the distribution, or the p hat that maximizes the beta distribution, happens to be alpha minus 1 divided by alpha plus beta minus 2. So the expected value is somewhat intuitive. It's just saying that as per my prior, the probability of heads was alpha divided by alpha plus beta. So alpha is like the number of heads I anticipated, and beta is like the number of tails I anticipated. And alpha plus beta is the support. And support for what? Support for my prior probability that alpha divided by alpha plus beta is the probability of number of heads. So we've just summarized this. Expected value of beta is alpha by alpha plus beta, and the mode of p, of the distribution for p, is alpha minus 1 divided by alpha plus beta minus 2. Now plotting the beta for different values of alpha and beta is very interesting. We find that when beta equals 1, you get a uniform distribution, something like this. When alpha plus beta equal to 1, which is alpha and beta less than 1, for example this red curve, you find that this distribution is bimodal. It peaks at 0 and 1. However, when alpha and beta sum up to greater than 1, then you find that a bell starts protruding gradually. So it starts peaking somewhere in the middle and tapers off. So the map estimate for the Bernoulli distribution can be obtained through application of the beta prior, and the map or map maximum posterior estimate is nothing but the mode of the posterior under the beta prior. And it turns out to be alpha plus h minus 1 divided by alpha plus beta plus n minus 2. And if you are interested, the expected value of p under the posterior is alpha plus h divided by alpha plus beta plus n. There's a kind of advantage we see from the use of a conjugate prior, that evidences simply keep adding up and the form of the distribution looks very similar to what it was earlier. The parameters are what keep changing. So to contrast, the maximum likelihood estimate did not consider any prior experience, whereas now you're considered prior experience. What does this mean for the coin tossing example? So he observed 4 heads on 4 tails and 4 tosses. So his MLE was 1. But suppose his prior was with alpha and beta equals 3. So then his posterior under this beta prior would be 0.75, which means that tails is not improbable under Bayesian assumption, or using the Bayesian estimation process. How do you apply all this to regression? Because that's what we set out to solve. So let's look at linear regression once again. Epsilon was normally distributed, mean 0, variance sigma square. We will use a prior distribution now, but on each wi. We'll assume that each wi is normally distributed with mean 0 and variance 1 upon lambda. This 1 upon lambda or lambda is basically 1 upon variance, and it is also called the precision. Higher the value of lambda, less is the spread. More compact is the interval in which you expect more points to lie, and more precise is your wi. So recall that this just means that each component wi is approximately bounded within plus minus 2, or you can take 3 times a 1 upon under root lambda. This is as per the 3 sigma rule. So now, what is Bayesian estimation for Gaussian distribution? What does it mean? With this prior on wi, how do I come up with posterior? So we'll benefit from considering a simpler version of the Gaussians. We have multiple wi's here. Let's try and deal with single wi's. So we'll illustrate on a single Gaussian and then move on to the case of multiple wi's or multivariate case. So we'll temporarily generalize the discussion with x taking the value of epsilon and mu taking the value of wi. This is roughly speaking. Now let the data be x1 to xm, each point or each instance being IID, the distribution, the Gaussian distribution mu, mean and sigma square variance. So we know that the maximum likelihood estimate is average of the points in the case of mean and in the case of sigma square. It's basically the average squared deviation. Now, the conjugate prior for the univariate normally distributed random variable, in the case that sigma square is not a random variable, is actually the Gaussian random variable, Gaussian distribution is a conjugate prior. Why? Well, we'll see soon, but let's assume that this is actually correct for the time being. So what would the posterior be? Well, we would expect that the conjugate prior gives you the same form for the posterior. So we would expect probability of mu given x1 to xm to be normal, but with a different mean mu m and different variance sigma square m. What should be the values of mu mb and sigma square mb? We'll see this in the next class. So next class we will derive the specific values of mu m and sigma square m. These mu m and sigma square m basically behave like weighted linear combinations or harmonic combinations of the respective older or data driven means and variances respectively. Thank you.